right. Hello. Some students requested that I explain a couple of questions from tutorial 9, right? So this is question 5 from tutorial 9. So here is what we're going to do here. So we need to use the power series representation for 1 over 1 minus x, so which is just a familiar geometric progression to derive well, a few other power series, right? So let me just begin with part A. Right, so in part A, we're going to need to find the power series for this function 2x divided by 4 minus 3x, right? So, and basically, the form that we're looking for is 1 divided by 1 minus something, right? So it's going to be uh, 1 minus something in the denominator. So, and in order to get 1 minus something, we basically need to take out uh, 1/4, right? So let me take out 2 and let me take out 4. So this is 2x over 4 times 1 over 1 minus. So to get 3, I need to multiply 4 by 3/4, right? So it's going to be 3x over 4. All right, and this is, in fact, 1 over 1 minus x, where instead of x, we just substitute 3x over 4. So it kind of plays the role of x. So you can think of this 3x over 4 as being like a new x, right? So and then what we're going to get, we're going to get 2x over 4 times, well, basically 1 plus 3x over 4 plus 3x over 4 squared plus 3x over 4 cubed, and so on. Yeah, and by the way, the original power series is valid one axis between -1 and 1. So this is valid. So this is defined and works if, well, now 3x over 4 plays the role of x. So it works whenever 3x over 4 is between -1 and 1. But then we can kind of simplify it if you want. So 2x over 4 is really just x over 2. Then this is the sum from 0 to infinity of 3x over 4 raised to the power n. Yeah, and again, so this works if 3x over 4 is between -1 and 1. So multiplying this by 4 over 3, we get minus 4 over 3 less than x less than 4 over 3. So this is the domain of our power series for this function. Well, but then if you want, you can again, so move x in, move 1/2 in. So this is going to be like sum from 0 to infinity, well, 1/2 times 3/4 to the power n times x raised to n plus 1, because x raised to the n times x is really x raised to the power n plus 1. And then if you prefer a series with powers of n rather than n plus 1, technically speaking, this is still a power series, but uh, if you want, you can basically replace, well, what you can do is you can kind of do something like this. So if you denote this by, say, t, right? So n plus 1, if n plus 1 is t, then n is really t minus 1. And if n changes from 0 to infinity, it means that n plus 1 changes from 1 to infinity, right? So basically, you can think of this as the sum from really like from t from 1 to infinity, and then 1/2 3/4 uh, raised to the power t minus 1 and x to the t. But then t is just a notation, right? So it really doesn't change anything. So if you want, you can change t to back to the n. Um, so that's the answer. Well, strictly speaking, I would accept the answer in this form, but if you prefer like a nice power series um, written with the summation symbol, and with powers of n, then here is the answer.